Okay.
Let us solve this statically determinate rigid jointed plane frame for drawing bending moment diagram, shear force diagram and axial force diagram. Now this is a hinged end A and this is a roller end D. There are 2 point loads acting and this part is inclined. All the dimensions are given. Now first, as usual, let us start with calculating the reactions. So if we see the whole frame, it is loaded in horizontal direction only by one load, that is a concentrated load of 15 kilonewton at E. Now already we know from basic engineering mechanics and strength of materials that the roller cannot develop or roller cannot offer any reaction parallel to its base. So I don't need to go for any summation of effects kind of thing. It is obvious that this 15 kilonewton disturbance has to be registered by a horizontal reaction at A alone, because roller cannot develop any reaction parallel to its base. So reaction here is 0. So it is obvious that this 15 kilonewton has to be counteracted by horizontal reaction at A, that is HA, which will be obviously 15 kilonewton. So you must observe one thing here, that I have avoided that summation of fx equal to 0 and all those kind of things, because it's really not needed. It's obvious that since roller cannot offer any reaction parallel to its base, so this hinge has a responsibility of offering reaction which is equal in magnitude to this 15 kilonewton and opposite in direction. Now next we have to calculate the vertical reactions at A and D. So I'll assume that both the reactions are upwards. So this is VA and this is VD. Now I can take summation of MA equal to 0 or I can take summation of MD equal to 0. So when I take summation of MD with clockwise positive equal to 0, you can also take anti-clockwise positive, it doesn't matter. So what does it give me? It gives me VA into 7, this VA into 7. I am taking moment at D, so D is my moment center. So VA is clockwise about D, therefore it is VA into 7. Then coming to this force, again, so when I take moment of this 15 kilonewton about D, its sense is clockwise, so it is obviously plus 15, and the perpendicular distance between the line of action of 15 and D is this 2 meter, therefore into 2. And then coming to this 10 kilonewton, that 10 kilonewton becomes anti-clockwise at D, and therefore it is minus 10 into 3, that is equal to 0. So it is minus 10 into 3 plus 2, that is 5. That whole equal to 0 to satisfy this equilibrium condition. So when we solve this equation, VA, that is vertical reaction at A, is 2.86 kilonewton. We assumed VA to be upwards initially and the answer came out to be positive. That means our assumption is correct. That means now we can finalize that whatever assumed direction is correct and the magnitude is 2.86 kilonewton. Had this answer been negative, I would have reversed the direction, but since answer came out to be positive, my assumed direction is correct. Now as a usual step, I will carry out summation of Fy upward positive equal to 0. What it gives me? It gives me 2.86 plus Vd minus 10 equal to 0. Therefore, Vd equal to 10 minus 2.86, that is 7.14 kilonewton. Again you have to see here that Vd initially assumed upwards, answer came out to be positive, that means my assumption is correct. So reaction Vd is 7.14 kilonewton. So we are done with calculating all basic reactions. Now we have to start drawing AFD, SFD and BMD by taking various elements of this statically determinate rigid jointed frame. Let us first start with element AB, that is vertical element, or you can say column. So how shall I do that? Very simple. Let me try to draw free body diagram. This is A, this is B, center point is E, and this is 15 kilonewton, 2 meter, 2 meter. Already I know that reaction here Va is 2.86 kilonewton. Now I want to show the details at joint B. So we know the equilibrium rule that for the whole structure to be in equilibrium, each and every point must be under equilibrium. Moreover, each and every element must be under equilibrium. So if I want my frame ABCD to be in equilibrium, that means AB must be under equilibrium. In other words, it means that the three equations of equilibrium must be satisfied for element AB. Going by that fact, it is obvious that if this Va 2.86 in upward direction has to be balanced by a downward reactive force of 2.86 kilonewton at B. That is, this force is equal in magnitude to this and opposite in direction. So again, when you apply summation of Fy to this element, this 2.86 upward minus 2.86 downward is 0. Again, we know that this reaction is 15 kilonewton here, that is Ha. Already I have calculated initially. Now it is very interesting to see that when I consider this element AB, this 15 is already getting cancelled with this 15. So the net effect of this 15 and this 15 is 0. Therefore the reaction developed here, the internal reaction, is 0. Because since this is getting balanced with this, there will be no any force getting developed here. This is not the only way how we can decide about these reactive forces. We can go from basics also. How I will show you. Now, going back to the original diagram, this Va is 2.86. Now, I want to know the internal reactive forces here at B, here. So, if I cut the frame imaginarily at this point and if I throw away part BCD, then This reactive force 2.86 kilonewton, what does it practically mean? 2.86 at B is nothing but it is the force offered by part BCD at B to part AB. That means when I cut this part BCD and throw it away imaginarily, then let us see what happens. This 10 in the downward direction and this 7.4 in upward direction. The net effect of these two forces is 2.86 in downward direction, because 10 is a greater force which is acting in downward direction, 7.14 is a smaller force. So 10 minus 7.14 is 2.86, and the net effect is in the downward direction because 10 is greater, which is acting in the downward direction. Therefore here 2.86 is in the downward direction. But every time we don't need to do all these things, that we have to cut and throw it away and we have to show the net effect at B. That is not necessary, because you have learnt in engineering mechanics, again I am repeating, that for the whole structure to be in equilibrium, each and every element must be under equilibrium. So it is obvious that this 2.86 must be counteracted by this 2.86. Same explanation can be even given for this 15 kilonewton. 15 kilonewton are out to 0. Let us again go back to this main frame. Now if I talk about horizontal forces, again when I cut this part and throw it away, on this part there is no any horizontal reaction. That means again when I cut it and throw it away, and when I want to show the effect of part BCD on AB at B, obviously the reaction will be 0. Now let us try drawing axial force diagram. So like you have learnt in strength of materials, let me first draw the axis A, E and B. Now this 2.86 is the axial force which is compressive in nature. Now the axial force, if you observe this element AEB, the axial force is same throughout and its nature is compressive. It is creating compression in the column. So you can use any sign convention, but for my convenience I will be using that compression is negative, and I will try to show it inside. Compression I take negative and I show it inside the frame. Therefore I will just draw 2.86 kilonewton. Here also it is 2.86 kilonewton. I am showing it inside because it is compressive and there is no change in axial force, therefore definitely it will be a rectangular diagram. It is negative. So this I can call it as axial force diagram. Similarly, I can go for shear force diagram, that is SFD. Now how to draw shear force diagram? Again you know from strength of materials. But here regarding the sign convention, again you can assume anything as positive, anything as negative, but again for convenience, the best way is always imagine that you are standing inside. Always imagine that you are standing inside, and then you have to draw SFD of this AB. So you are looking to this column. So obviously this becomes your right and this becomes your left. So when you apply this theory here, now this is the inside part of frame. Because of 15 kilonewton, left is going up. Actually it's going outside, but you can just imagine that is a horizontal element. Left is going up, and you know that left is positive. Left up is positive. Now again you draw it. A, E, B, positive entities I show it outside the frame. So left up is positive, so it is 15 kilonewton. Then we know that at E there is one point load of 15 kilonewton. So whenever there is a point load, you have to take shear force just below it and above it. So since there is no load between A and E, the shear force will remain same. So shear force just below E will be again plus 15 only. But if you take shear force just above E, then it is interesting to see that it is this 15 minus 15. So it is 0. And if you see part B, there is no any force in this part B. This internal reactive force is 0 and there is no any transverse force in this direction. Therefore, obviously shear force in part B is 0. So this is a correct SFD with the sign conventions which I have assumed. You can assume different sign convention whatever convenient. It's not necessary that you should stick to my sign convention. Now coming to very important, that is bending moment diagram. Let me once again try to draw the frame. I mean part of frame AEB. Now we know that bending moment at A, that is a hinged end, is 0. Now coming to bending moment at E. So again coming to the main diagram. What is the definition of bending moment? Definition of bending moment is, it is a moment which is trying to bend that element, and it is obtained as algebraic summation of moments of all the forces including reactions either lying on one part or on the other part of the structure. So the other part is somewhat complicated. It's not actually complicated but somewhat time consuming. So let us go for this simple part, EA, because I have a liberty to either consider EBCD or AE. The definition of bending moment gives me that flexibility and that freedom. But from convenience, comfort and ease point of view or time saving point of view, EA will be better. Now what is the sign convention? Very simple. Again you have to stand inside. Now I want to take bending moment at E. Again sign convention can be as per convenience of different students, but the better way is, if the force is causing this part to open out like an umbrella, then you can take that bending moment as positive. And if the force is causing this part to close, then you can take it as negative. Now we know that VA is axial at A, it is not creating any bending moment since there is no perpendicular distance. Now coming to horizontal reaction 15, it is trying to open out part EA. So you can say ME, that is bending moment at E, will be 15 into 2 positive, that is 30 kilonewton meter. Already I told you that bending moment at A is 0. Now coming to point B, again as per the definition of bending moment, I have a liberty to consider either part BCD or part BEA. But again part BEA will be simple. So let us consider. Again VA is not creating any bending moment at B because it is axial. HA is trying to open out this like an umbrella. Therefore MB will be 15 into perpendicular distance is 4 And interestingly, you have to observe that this concentrated load 15 at E is trying to close this part BE, which is exactly opposite to this action, and therefore it must be negative. That is minus 15 into 2. So it is 60 minus 30. So answer is plus 30. Therefore, MB equal to plus 30 kilonewton meter. And now you can complete the bending moment diagram. This is 0, this is 30, and interestingly here also the bending moment is 30. So here the bending moment is changing from 0 to 30 and then it is remaining constant. And always we don't need mathematics and equations. It is very easy to understand because part B is free of any shear force. And therefore the bending moment is constant because we know that shear force is nothing but rate of change of bending moment, that is F equal to d dx of m. From E to B shear force is 0 and therefore shear force is 0. That means bending moment must be constant because d dx of constant is 0. So obviously without calculation also, as a student you should understand that once the shear force is 0 for a certain part, bending moment must be constant. If this answer would have been anything other than 30, that means you have made some mistake. Similarly, here the shear force is constant, 15 here, 15 here, therefore bending moment is having a linear line. Now this is positive, this is positive. So this is BMD. Now going to part BC. Let me try to draw free body diagram of BC. Now again it is very simple, equilibrium rule. Now if you compare or if you take diagram AB, now I know that this was 0. So again here this must be 0 because in engineering mechanics you have learned that for the whole structure to be in equilibrium, each particle must be under equilibrium. So when this reactive force was 0, this must be 0. Now again at C, this must be 0 because if BC is to be in equilibrium in horizontal direction, I mean if you want summation of effects to be satisfied for element BC, and if this horizontal reactive force is 0, this must be 0. Now again going back to this 2.86 kilonewton in downward direction at B. So when you draw free body diagram of BC, you just reverse the direction 2.86 kilonewton. The explanation is again same, that is 2.86 downward at B and 2.86 upward at B. When I join these two parts, again the effect is 0, 2.86 upwards minus 2.86 downwards. That means this point B also must be in equilibrium. That means if I apply summation of Fy to B, 2.86 minus 2.86 must be 0. Again it is obvious that there is one 10 kilonewton load already given in the problem in the downward direction. Therefore, if I want to calculate the reactive force at C, very simple. This 10 kilonewton downwards minus 2.86 upwards. So the net effect of this is nothing but a downward force. That means if I subtract 2.86 from 10, it is 7.14 kilonewton. And to resist this 7.14, here part CD has to offer an upward reaction force of 7.14 kilonewton. So that now this 2.86 plus 7.14 is 10 and this is 10. So both these upward and downward they cancel, and therefore summation of Fy can be applied. Okay, now I will take this point as F for convenience. Now let us start drawing AFD, SFD and BMD. So we know that this beam element BC is free of any axial force, neither compression nor tension. Therefore, there will be no axial force, and obviously AFD diagram will be like this. Now coming to SFD, I know that this part B, because of 2.86, B is going up. So left up is positive. I show it outside. So 2.86 kilonewton up. Now part BF is free of any forces. So we know from strength of materials that the shear force remains same. So the shear force just left of F will be same as 2.86. But when I go to just right of F, again as per the definition of shear force, it is algebraic summation of forces including reactions either lying on one part or other part of the element. So if I consider right part, because of 7.14, this right part is going up, right up is negative. Therefore suddenly just right of F, the shear force goes to minus 7.14 kilonewton. Now again there is no any force between F and C, therefore shear force must remain constant. Or other way also, this 7.14 is causing C to go up, so right is going up, so that is also, that explanation is also okay. So minus. So this is SFD. Now for BMD, it is always better to go to the main diagram, because this free body diagram I only draw for SFD and AFD. For BMD you can always go back to main diagram. Now there is no necessary to calculate bending moment at B, already you have calculated. Bending moment at B is 30 kilonewton meter. Now next will be bending moment at F. So again there are two options. You have got a liberty of either considering FBEA or FCD as per the basic definition of bending moment. Now considering FCD will be more convenient and time saving. So let me try that. So bending moment at F will be this 7.14 into perpendicular distance is 5, because this is 2 meter, And if you see keenly, this 7.14 is trying to open up this part of CD like an umbrella. Therefore, as I told you in the beginning, I can take it as positive. Therefore, MF will be 7.14 into 5. The answer is 35.72 kilonewton meter. Now coming to bending moment at C. Again I can go back to the main diagram. Again, as per the definition of bending moment which you all learnt in strength of materials, either I can consider part C of BEA or CD. But again, there is no point in considering C of BEA, that is time consuming as well as there are chances of making mistake. So to save the time and not to make mistake, you can consider part CD. So when I take bending moment at C, again if you observe, this 7.14 is trying to open up the part CD like an umbrella, and I take it as positive. So again MC will be 7.14 into perpendicular distance is 3, that is 21.44 kilonewton meter. So very easily now I can draw the bending moment diagram. This is B, this is F, this is C. Now bending moment at B is already positive 30 kilonewton meter. So it is 30. Bending moment at F is 35.72. So 35.72 kilonewton meter. Now how to join these 2 points? Now if you go to shear force diagram, it is constant, and again you know that F is d dx of M, that is shear force is rate of change of bending moment, and therefore I have to draw a line, I have to join in such a way that this equation gets satisfied. So when shear force between these 2 points is constant, that obviously